Hi guys, we're going to cover section C for chapter 16, kind of a short section, starts on page 387, to kind of wrap up our talk of fluids, okay? So the first thing we're going to talk about is, let me put myself right there, is hydraulics, okay? So hydraulics take into account this idea of pressure being equal to force over area, okay? It also uses Pascal's principle, okay? So if I exert a pressure on this confined fluid. So hydraulics, oh, come on, where's my pen? There we go. Hydraulics are basically tubes filled with a fluid, okay, with like a liquid, a kind of a thick liquid. If I exert a pressure on that confined fluid, Pascal's law tells me, or Pascal's principle tells me that that pressure is going to be spread throughout all of the fluid. It's not just going to be right here. It's going to be throughout all of the fluid. Okay, so because of that, I know that the pressure that results from my input force is going to be the same as the pressure that's exerted on the output side. Okay, I'll plug some numbers into that and it'll make a little bit more sense. Okay, this also works because liquids do not compress. While gases will compress and get closer together, the particles of a liquid do not compress. You cannot change the volume, okay? That pressure is going to move things. So hydraulic fluid fills an airtight system. It's got its volume, it's got its pressure, and it cannot compress. Okay. So what hydraulics do is they magnify a small input force to produce a larger output force. So this is our input force, and this is our output force, okay? You can lift a car out of mechanics. This is how your power brakes work in your car. I'm going to try to plug some numbers into this so it makes a little more sense to you, okay? And I'm just going to make these numbers up, okay? So I've got my pressure equation right there, okay? So if I have an input force of 10 and the area of the piston that I'm initially pushing down on has an area of 5, that's going to give me an initial pressure of 2. Again, I'm just making up these numbers, okay? Because of Pascal's principle, I know that the pressure is going to be the same all throughout this system, okay? So now I've got this second equation here. My pressure is 2. Now I've got this much larger piston. In fact, it's 10 times as big as what I started with. So now I'm going to put a 50 there. And so I'm going to calculate what my output force is going to be, okay? What divided by 50 gives me 2? Well, that's going to give me 100. So look at what happened to my force. My input force of 10 became an output force of 100 based on the way these hydraulics work. So you can see how a little bit of input force can be magnified if you increase the area on the other side of the hydraulic system, okay? All right, let me move myself back down here. We have another principle to talk about, okay? Notice that these are spelled L-E. These are not like the principle of Mr. T, okay? These are kind of like science rules, all right? So Bernoulli's principle relates moving fluids, and it tells us that the faster moving fluids actually exert less pressure than slower moving fluids, okay? And you can see this with a simple piece of paper, okay? Got my March Magnus bracket. And I'm going to blow over the top of the paper, and I'm going to turn sideways so you can see what happens. As I blow over the top of this paper, that's going to be a faster moving fluid than the fluid underneath, okay? Remember, gas is a fluid. Hopefully you can see that. The paper's moving up, okay? And the reason for that is because of Bernoulli's principle. So let me explain that to you, okay? You can see it on a wing as well, okay? So let's see. Air is moving this way over a wing. And it has a farther path to travel over the top of the wing than it does underneath the wing, okay? So that means that the air on top has to go faster. Otherwise, it wouldn't meet up at the end of the wing at the same time, and you'd have a vacuum, and nature doesn't like vacuums, okay? So the air on top has to go faster. Based on Bernoulli's principle, faster moving fluids have lower pressure, okay? So the faster air on top has a lower pressure, then the slower air on the bottom, it has a higher pressure, okay? When I blow on the paper, the faster air on top has lower pressure than the bottom. Slower on the bottom, higher pressure. High pressure always wants to move to low, okay? So lower pressure on top due to faster speed than below, higher pressure moves to lower pressure, okay? So for the paper, the higher pressure from the slower air on the bottom is going to move the paper up. It's trying to get to the lower pressure on top. With a wing, this lower velocity, the slower air on the bottom with the higher pressure, it's actually going to start pushing up, trying to get to this lower pressure environment, and that's known as lift, okay? So the wings of airplanes are shaped like this to help keep them in the air. It doesn't help, it's not what gets them up there. Engines and thrust and all this other crazy stuff get them up there. But the shape of the wing helps to keep the airplanes in the air. This is also why birds can kind of glide through the air without flapping their wings, because their wings are also shaped with a curve like this. If you look at the spoiler on the back of a race car, watch my amazing drawing here. Okay, here's a spoiler. Boom. It's going to look like an upside down wing. Okay, so it's going to be flat on top and curved like that. Okay, and so the air underneath will be going faster. The air above will be going slower. Slower means higher pressure. So now all of a sudden we've got the high pressure pushing down. And what that spoiler does is it helps keep these back wheels with good traction and better friction on the track. So that's how the spoiler of a car works, okay? All because of Bernoulli's principle. Boom, done. See ya.